Another device that relies heavily on Faraday's law is the electrical transformer. And let's take a look at that in this segment. First, I'm just going to consider the following. This is sort of a crude transformer, I suppose. We'll see exactly how to do it. But I'm going to think of a long, hollow tube, and I'll have insulated wire. I'll have one of them that is hooked up to one of these electrical generators that's generating E at some frequency here. And I'll assume that it's wrapped in P times. The P is for primary. Usually the one that has the voltage source in it is called a primary. And it has a number of terms here. Now I've got a reduced number, and another thing I've sort of taken some artistic license is these should be intermingled, the primary and the secondary coils. But so think of this really as going over the whole length of this. They're insulated, so there's nothing that can interfere with one another. And then this other coil over here, really it just has a coil of wire wrapped around the same tube, and then something to use the power. I just put a resistor here for it. The area that it encloses, that's the cross-sectional area. Let that be A. And again, really these are all over this whole length, because usually NP is very large and NS is very large, and so they intermingle these all the way around. But they're insulated, and so they, in a sense, they're separated, and I've separated them here. Now you just have to take a little bit of artistic license, and we'll do that here because I think it's a little easier to see. I'm gonna we know that this current is alternating back and forth here because it's produced by this AC generator, and I'm going to catch the current when it's going in this direction. And this is IP that's in it at that instant. The number of turns is NP, and the P for primary. And I know what happens. It's simply a solenoid. Okay? And current produces a magnetic field. And if you use your right-hand rule, the magnetic field is going toward the right when I catch it at this point. Now, of course, part of the time it's going one direction, and part of the time we're going the other direction. So this magnetic field, sometimes it's getting stronger, and then it gets weaker, and it points in the other direction. So as the current oscillates in different direction, the magnetic field direction, I just happen to have caught it in this form here. And in fact, I'm going to be catching it when it's not only going in this direction, but it's getting stronger. So it's on the upward swing of currents over here in that sinusoidal. And so the magnetic field here is getting stronger and stronger and stronger. And I know magnetic field changing with time induces, by Faraday's law, a changing flux through this loop over here, this coil over here. And it will then provide an induced current in this, which would be I sub S. And if you look at it, if this is increasing, it will induce a current in the direction to oppose that increase, which would be in the opposite direction. Now, if it's decreasing here, so then it goes in a different direction. So I've only caught it in one direction here while it's increasing, but going in this fashion. I could have a different number of turns. Again, the secondary coil is the coil that doesn't have the generator in it, in our view. And so N sub P and N sub F are different. And as a result, we get an induced current over here of I sub S. Well, you can get IP. It's just the EMF produced by the generator here, divided by whatever the total resistance is in all of this. And there's actually a fair amount of resistance because, remember, these electrical generators involve a coil of wire, so they might be a fairly lengthy thing. So at any event, you get a sinusoidally varying current that oscillates back and forth. The magnetic field that this produces is really B sub P. And remember, that's mu naught or N, little n times IP. That was the formula we had for a solenoid, for the magnetic field produced by the solenoid. And so this IP produces this magnetic field that's mu naught times the number of turns divided by the length, where the length is presumably the whole length of this solenoid. That produces the magnetic field down the center. And so the magnetic flux that's produced over here in the secondary through one coil is just B times A. It's one direction. I'm choosing my area normals to be to the right in this case. And the magnetic field that does that is the one that was produced by the primary coil. So that's mu naught NP over L times IP, this one. And then to get the flux, I just have to get the area enclosed, which is just that cross-sectional area. And then I'm really set up for it here to get the induced current in the secondary coil, or the induced EMF. It's the number of turns times the time rate of change of the magnetic flux. So the magnetic flux is created through this coil is from the magnetic field is created by the primary coil. Well, you can plug that in. You have lots of constants you can pull through, but basically what's induced in the secondary is, I really ignored the negative sign here. It's in the opposite direction. That's really what this negative sign is. So from here on, I'm just looking at magnitude, and it becomes this expression for the EMF in the secondary coil. And so you could have the generator going, and have a light bulb or something here, and it would light up. So, well, that's the basis of an electrical transformer. An electrical transformer is a little bit more complicated, in that we have over here the primary coil with an AC generation. It has a number of coils in it, NP. On this side is the secondary that has a number of coils N sub S, so the secondary coils over here. I think it's a little bit different is that they have usually an iron block around with a hole cut in it like this. And the reason for that is that the magnetic field that comes in, the iron magnetic moments will, and its various atomic domains will line up with it. And so it tends to keep this magnetic field trapped going around this at the same magnitude. Now, of course, this is changing probably 60 times per second. So sometimes the magnetic field is going this direction, sometimes it's going the other direction, due to the alternating current. But we can use Faraday's law for the primary and the secondary. For the primary, I know that the flux through the primary is minus NP, the number of turns in the primary, times the time rate of change of the magnetic flux that's going through here at any given time. And that gets transmitted around over here so that the same magnetic field is cutting us. I'm assuming they have the same area, but they wouldn't have to. And so the EMF that's generated in the secondary coil is, again by Faraday's law, is minus N sub F times PB. But it's the same flux that's going around because it's the same magnetic field, same thickness, same cross-sectional area. And so I just take the ratio of these two, E sub S over EP, and that just becomes N sub F times this derivative, negative over minus N sub P, this one. And it's the same flux, so the time rate of changes of those is the same. Negative signs go out, and you get that ratio is really equal to NS over NP, or the secondary voltage, EMF, is the same as this ratio N sub S to N sub P times the primary voltage. Well, that is very useful. And for one thing, I might be easier to generate electricity at very high voltage over here. But if I want to use something, I don't want to have deal with high voltage over here. And so I would choose one that maybe has 100 turns over here and 10 over here. And so then I would get 10 over 100 and get 1/10. So if this was 100 volts, I would get over here on this side just 10 volts. You know? Well, for an ideal transformer, there is no energy loss. Now, really, there is pretty substantial energy losses because if you think about it, the iron magnetic dipoles are switching directions with the frequency of this. So, part of the time they're pointing with the field. They always try to point in the direction of the field, but the field switches, and so they're flopping back and forth, and that tends to heat up these. And so, usually these have to be well insulated and have something to dissipate that heat. Yeah? But if we assume that there's no heat losses and have an ideal transformer, then all of the power that's delivered to this by the primary gets sent over to the secondary. And that's the electrical power, which is time rate of change of energy. And remember, power is I times V, and in our case we have the current in the secondary times the voltage in the secondary is equal to the power in the primary, which is just I times V, the current in the primary times the voltage or the EMF in the primary. And if you rearrange those, you can solve for IS. Well, if you solve for IS over IP, that becomes IP over EP over ES. And remember, we just, from above up here, we have the ES is N sub S over NP. And so here the EPs go out and then it flips over. And so you get the current in the secondary is equal to NP over NS times the current in the primary for an ideal transformer. What that means is that if I step down the voltage, what happens? Well, if I said this was 10, or if this was 100 and this was 10 wraps over here, I would have 10 over 100, and so I would reduce the input voltage in this transformer to something less. If this were 120 volts, I would have 1/10 of 120, and over here the highest we'd ever get would be 12 volts, 1/10 of 120. But at the same time, what happens? Well, this is the current in the secondary goes up. NP is 100. The N sub S is 10, and so this becomes 100 over 10. And so the current increases in the secondary by a factor of 10 over the primary. And in general, that's what happens with these. If you decrease the voltage, you increase the current. On the other hand, you could arrange things to have a step, that would be a step-down transformer. A step-up transformer, maybe you want to create high voltage, and so you would have the N sub S a large number and the NP small, and that would then create a higher voltage over in the secondary if N sub S is larger. If N sub S is 100 and this is 10, you could increase the voltage on this side by a factor of 10, for instance. Well, those are the two cases. The circuit symbol for a transformer is this diagram, and I've left out, there's other things over here that would be other parts of the circuit, but there's no connection between them, really, in the sense that they're separate circuits, but yet because of Faraday's law, we're transmitting the power from one side to the other. If N sub S is less than N sub P, you have a step-down transformer, and if N sub S is a larger number of wraps than N sub P, then you have a step-up transformer. Just some language associated with it.